This is Chakradhar Rao Konda, and this is my project presentation of the course CS512 Advanced Operating System. Uh, the project name is VSMT-IO, Improving IO Performances and Efficiency on SMT Processor in Virtualized Cloud. Coming to the main introduction of this part, the modern computing world, with its widespread use of simultaneous multi-threading, SMT in short, processors like hyper-threading on x86 architectures presents a significant yet overlooked challenge: efficiently scheduling input and output workloads. SMT processors are crucial for cloud infrastructures, improving resource utilization and system throughput. However, currently central processing unit CPU scheduling techniques optimized for I/O performance are proving ineffective on SMT processors. The main problem arises from the excessive context switches and spinning caused by current CPU scheduling. When I/O workloads are waiting for events, this efficiency hampers achieving both high CPU and input-output throughputs, which are vital for the demanding workloads common in cloud environments. The challenges becomes even more pronounced in virtualized clouds, where I/O and computational workloads share the same server. In recent paper by GAA-ETL published in 2020, the limitations of existing techniques are identified, and a new approach called VSMT-IO is proposed. The primary focus is on optimizing I/O performance on SMT-enabled systems, particularly on x86 processors commonly used in virtualized clouds. Significance importance of the study. The importance of addressing I/O performance inefficiencies on SMT processors becomes clear in the context of prevalent cloud computing practices. In modern cloud infrastructures, virtualized instances often combine intense I/O operations with computational demanding tasks, making the need for efficiency schedule techniques crucial. And current solutions designed primarily for the computation in intensive workloads fall short when dealing with simultaneous challenges of flow computation and I/O operations. This leads to a performance bottleneck that hampers system throughput and resource utilization, directly affecting the scalability and responsiveness of the cloud services. The significance of this study extends to its focus on virtualized clouds and x86 processor, recognizing their dominance in contemporary cloud environments. The proposed VSMT IO framework aims to address the existing gaps in IO performance and maximizes the system throughput while minimizing the context switching overhead. This is not only improves the efficiency of the cloud but also contributes to the overall scalability and responsiveness of the cloud computing systems. Coming to the summary of this paper, in short, in the current landscape of the cloud computing, simultaneous multi-threading SMT processors like hyper-threading on x86 architectures play a crucial role in improving resource utilization and system throughput. Despite the benefits, scheduling input-output workloads on this processor remain a significant challenge, calling for innovative solutions. This paper addresses this challenge by presenting a comprehensive study that identified the address and limitations of the central processing units, scheduling techniques, particularly when applied to I/O workloads. On SMT processor, the main issue stems from inefficiency introduced by context switching and spinning during I/O operations, impairing the attainment of high CPU I/O throughputs essential for modern environment cloud environments. The proposed solution, VSMT-IO, introduces a novel approaching that specifically focuses on optimizing I/O performances on SMT-enabled systems. with a particular emphasis on x86 processors commonly used in virtualized cloud environments. The study begins by articulating the problem statement, emphasizing the need to address the challenges posed by I/O workloads in the context of SMT processor. The main aim of the paper. The motivation behind this subject study stems from pressing need of address performance gaps related to I/O intensive workloads and SMT processors. In the dynamic landscape of cloud environments accommodating the diverse workloads from database management systems to artificial intelligence tasks, exposes the limitations of current CPU schedulers in meeting these varied demands. The SMT IO framework proposed in this paper is motivated by goal by enhancing overall cloud efficiency. It aims to provide a tailored solution for addressing IO performance bottlenecks on SMT processor, acknowledging the diverse nature workloads in cloud environments. In summary, the paper offers a comprehensive exploration of the challenges posed by IO workloads on SMT processor within virtualized cloud environments. This research not only identifies problems but also provides motivated and significant solutions, contributing to the advancement of the scheduling techniques in the context of modern computing architecture. The main aim of the paper. The primary objective of this paper are centered around tackling and complex challenges associated with I/O workloads on SMT processor with virtualized cloud environments. The key aims can be summarized into two main goals. First, one is understanding and articulating challenges. To elaborate this, the paper seeks to comprehensively understand and articulate the bottleneck present in the current CPU scheduling technique when applied to I/O intensive tasks on SMT processor. It aims to shed light on inefficiency caused by context switches and spinning during I/O operations, which impede optical CPU and I/O throughputs. Coming to the second aim, introducing and evaluating SMT VSMT I/O framework. The second objective is to introduce and evaluate the effectiveness of the proposed SMT I/O framework. The SMT I/O framework is designed to address these identified inefficiencies and enhance overall system performance in virtualized cloud environments. This paper, by providing a clear problem statement, emphasizes the critical need for tailored solutions in the domain of I/O scheduling on SMT processor. Coming to the next slide, significant contributions of the paper. The paper highlights efficiency challenges in current CPU schedulers when applied to boost I/O performance on SMT-enabled systems. It introduces the innovative concept of context retention as a method to enhance the efficiency of CPU scheduling for I/O operations, aiming to improve the overall performance of the systems utilizing SMT processors. Furthermore, the paper takes a practical approach by building a system prototype based on KVM, providing a tangible solution to the identified efficiency issues. This not only contributes a theoretical framework but also offers a hands-on, the implemental solution to enhance the efficiency of CPU for I/O operations on SMT-enabled virtualized cloud environments. This is the overall overview, the proposed system of vSMT-IO. The architecture of the vSMT-IO looks like this. And the key components are mentioned in the orange boxes. And coming to the overview of the proposed system, The architecture of ESMT is built upon four essential components, each intricately designed to address efficiency challenges in existing CPU schedulers within SMT-enabled systems. Long-term context retention mechanism, LTCR. Located in each core, LTCR is the cornerstone of the architecture. It enforces context retention, ensuring that retained context do not lead to excessive overhead during the prolonged periods. Retention-aware symbiotic scheduling algorithm. This algorithm takes a central role in maximizing symbiosis level among virtual central processing units, vCPUs, on hyperthreads. Through unbalanced scheduling, the RAS intelligently categorizes vCPUs into CPU bound and IO bound, aiming to optimize the resource utilization. Coming to the third one, workload monitor. This one, the workload monitor observes vCPU executions, characterizing workloads and providing essential performance metrics for both RAS and subsequent workload adjuster. Continuous monitor enables dynamic adjustments within the system. And coming to the fourth main component, workload adjuster. The workload adjuster is crucial for maintaining workload heterogeneity across the course. By periodically accessing the deviations and the context retention rates, the adjuster prevents performance degrading by orchestrating intelligent CPU swaps between cores. Coming to the working mechanism of the VSMT IO. The working mechanism VSMT is designed to optimize CPU scheduling and improve IO performances on SMT-enabled systems. Here is an overview of how it works. The long-term context retention, LTCR. VSMT IO utilizes a monitor M-weight support on x86 processors to implement vCPU's context retention. The LTCR mechanism manages the context retention overhead by dynamically adjusting context retention timeouts using algorithms. 1. Coming to the retention awareness symbiotic scheduling, RAS in short, focus on maximizing computation throughput. The RAS algorithm employs a two pronged strategies. Unbalanced scheduling intelligence classifies vCPUs to ensure optimal overlap between the computation and context retention periods. This dual approach enhances overall core performance by intelligently managing the CPU resources. Coming to the slide. Overview, the benefits and drawbacks of VSMT IO. Number 1, benefits. Enhanced CPU performance. VSMT IO intelligently schedules CPU bound and IO bound vCPUs. Maximize the symbiosis levels. Minimizes context retention overhead, leading to the improved overall CPU performance. Dynamic workload adjustment is the second benefit. Adapts to the changing workload through the workload adjuster component. Maintains heterogeneity across the course, preventing performance degradation over time. Drawbacks of VSMT IO. Complexity in implementation. The implementation of the context retention and the symbiotic scheduling involves intricate mechanisms. Potential challenges may arise in this real-world deployment and integration due to the system's complexity. The methodology of the paper. Study design. The research adopts an experimental study design, a crucial choice for addressing the complex challenges presented by VSMT-enabled systems. This approach involves the engineering of the tangible prototype of VSMT IO within the Linux or KVM environment. The implementation requires substantial modifications and encompassing around 1,300 lines of source code with a primary focus on KVM kernel, modules, and Linux completely phased scheduler, EFS. Key elements of the study. Hands-on implementation. The experimental design involves hands-on implementation, allowing researchers to actively engage in the development of the VSMT prototype. Approximately 1,300 lines of source code were modified, showcasing a substantial and practical commitment to bringing the proposed solution to life. Deeper understanding, the hands-on implementation facilitates a deeper understanding of how VSMT-IO behaves in real world. And the real world context, study design emphasizes the real world context design enabling the examination of VSMT-IO's performance in practical environment. Experimental setup. The detailed description of the experimental setup serves as a crucial foundation for interpreting the outcomes of the study. Key elements of the setup include server specifications. Utilizing a Dell PowerEdge R430 server, basic hardware specification include two Intel Xeon E5 2690 processor, each with 12 physical cores. And the operating system, Ubuntu Linux 18.04 is selected as both the host and guest operating systems. And workload diversity, a diverse set of workloads a diverse set of workloads from the various domains is employed in experiments. This inclusion enhances the ecological validity of the study, reflecting the real world scenarios where systems handle a variety of workloads. Significance of the setup. It provides a robust foundation for potential future studies in the field of system optimization, contributing to the advancement of the knowledge in this domain. Coming to the results, the key findings, the study's key findings underscore the substantial efficiency of VSMT-IO in enhancing IO performance within the in, intricate landscape of the SMT-enabled system. Some notable results include consistent improvement in IO-intensive workloads. VSMT-IO consistently improves the performance of IO-intensive workloads, achieves performance levels comparable to polling, a widely recognized technique for IO optimization. Remarkable efficiency is the second most key finding. VSMT-IO demonstrates remarkable efficiency in achieving improvements. Consistently outperforms alternate solutions like polling and halt polling in computation-intensive workloads. Coming to the data presentation, the study's data presentation is categorized by clarity and comprehensiveness, significantly contributing to the accessibility and interpretability of the findings. Several aspects of the effective data present include, include such as diverse figures and tables, integration of diverse figures and tables facilitates a nuanced understanding of the performance dynamics under the different scenarios. Coming to the second point, visual representation of the comparative performance. Visual aids like figures offers a quick and intuitive grasp of VSMT IO's impact. Normalized throughput of the benchmark, for example, provide a clear visual comparison, enhancing understanding. Number three, granular view of the system behavior. The tables detailing the number of vCPU switches, time spent at different states, and benchmark specific results offers a granular view of the system behavior. This level of detail allows readers to dwell into the intricacies of VSMT-IO's performance across a spectrum of workloads. Reinforcement of the key findings. Meticulous data presentation serves to reinforce key findings, visual aids and tables, provide supporting evidence for the study conclusion, and adding to the overall credibility of the research. Mm, Coming to the next slide, strengths of the paper. Research gap fulfillment. This paper admirably addresses significant research gap by identifying and rectifying the efficiency issues in existing CPU schedulers concern IO performance on SFT-enabled systems. Unique contribution, the paper's distinctive contribution is evident in the introduction of innovative concept, context retention, and the intricately designed long-term context retention (LDCR) mechanism. And the next one is objective achievement. The author successfully achieved their stated objectives evident in comprehensive evaluation that encompasses the real-world application with a diverse set of 18 programs. Versatile applicability. The inclusion of a diverse set of programs and experiments highlights the versatile applicability of the proposed VSMT IO systems across various workloads. This not only reinforces the system's potential for real-world applications, but also broadens its relevance in handling the different types of computational tasks. And coming to the weakness of the paper, evaluation scope. While the evaluation is comprehensive, extending the exploration to additional scenarios or workload variations would further validate the robustness of the VSMT IO. Targeted architecture. The paper predominantly focuses on virtualized cloud and x86 processors, potentially limiting its immediate applicability to other architectures or competing environments. Addressing the system's adaptability to different architectures would strengthen the paper's relevance across a broader spectrum of computing systems. Extreme conditions. I'm sorry. The paper could benefit from exploring the performance of the proposed system in specific case or extreme conditions, investigating how VSMT IO behaves under extreme workloads or resource constraints would provide a more nuanced understanding of its capabilities and limitations. Addressing these considerations would not only enhance the paper's completeness but also contributes to a more true understanding of VSMT IO's performance across various scenarios, architectures, and conditions. Coming to the next slide, open-ended questions. Adaptation of adaptation to emerging technologies. Uh, an open-ended question is how well VSMT adapts to emerging technologies and advancement in hardware architectures. Specifically, how does VSMT perform and adapt in the context of evolving hardware technology? Impact on energy efficiency. Exploring the energy efficiency implications of VSMT raises the question, how does VSMT influence the energy efficiency of SMT-enabled systems? And what are the potential environmental impacts? And the other two, security implications and user experience and considerations. Coming to the conclusion part of the project, the paper introduces VSMT IO as a groundbreaking solution to address the efficiency challenges in CPU schedulers on SMT-enabled systems. The study not only identifies these challenges but presents context retention as an innovative remedy. The robustness architecture of VSMT IO incorporating LTCR, RAS, workload monitor, and workload adjuster may mark significant milestones in the field. The implementation of VSMT IO evaluated across the various workloads showcases substantial improvements in both IO and processor throughputs. The finding revealed remarkable enhancement with up to 8.3% improvement in IO throughput and 123.1 improvement 123.1% improvement in processor throughput. In essence, VSMT IO not only effectively addresses existing inefficiencies, but also propels to advancement in CPU scheduling for SMT-enabled systems. This paper's contribution extends beyond identification and remedy, providing concrete evidence of positive impact on VSMT IO system performance. This work opens new avenues for the optimization of SMT-enabled systems, showcasing the potential for practical implication and significant improvements in both IO and processor throughput. Thank you.